Hello everyone, and welcome to today's webinar in the CERDP and ESTCP webinar series. My name is Rula Deeb. I'm a Senior Principal at Geosyntec Consultants in Oakland, California, and the coordinator of the webinar series on behalf of CERDP and ESTCP. I will be facilitating today's call. The webinar will consist of a brief overview of CERDP and ESTCP by Dr. Andrea Leeson, followed by a list of upcoming webinars in the series. After Andrea's opening remarks, we will transition to the technical portion of the webinar. Today's event features 3 speakers on research and development needs to manage Department of Defense sites contaminated with per- and polyfluoroalkyl substances, or PFASs. The first speaker will be Ms. Maureen Sullivan from the Office of the Assistant Secretary of Defense for Energy Installations and Environment. She will provide opening remarks about DoD policy and management issues associated with 2 key PFASs, PFOS and PFOA. Her presentation will be followed by a brief question and answer session. Next, Dr. Leeson will describe CERDP and ESTCP's efforts on gaining a better understanding of issues associated with PFASs in the subsurface. Her presentation will also be followed by a short Q&A session. Finally, Dr. David Sedlak of the University of California, Berkeley will discuss research efforts on remediating groundwater contaminated by PFASs using in situ chemical oxidation. We will conclude the webinar with a question and answer session with both Dr. Sedlak and Dr. Leeson. Because we have over 1,000 callers on today's webinar, the broadcast will be listen only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we do encourage you to submit questions well in advance of the Q&A sessions. On this slide, we have provided a few suggestions in case you experience difficulties with the broadcast audio. Typically, any delay will be fixed if you refresh your screen. Alternatively, you can call into the conference line. If you continue to have problems, please submit a comment using the chat box in the lower left-hand corner of the screen. With that, I would like to introduce Dr. Andrea Leeson, who is both the Deputy Director of CERDP and ESTCP and also the Program Manager for the Environmental Restoration Program with CERDP and ESTCP. Andrea, please proceed.
Thanks, Rula, and welcome everyone to today's webinar. Before we jump in, I'd like to give you a little overview of who we are in CERDP and ESTCP. CERDP is the Strategic Environmental Research and Development Program, and it was established in 1991 by Congress as a partnership between the DoD, the Department of Energy, and the EPA. And our mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. We fund both fundamental research as well as advanced technology development under CERDP, and the goal is to ultimately impact our real-world environmental management issues. Slide 10. ESTCP is the Environmental Security Technology Certification Program, and under here we demonstrate innovative environmental and energy technologies. And generally, what we're funding under ESTCP capitalizes on past investments that we've made under CERDP or other research programs and are designed to transition our technologies out of the lab and into the field. Especially important in all of our demonstrations is that we transition to implementation and regulatory acceptance. CERDP and ESTCP are complementary programs with much of CERDP research occurring at the lab and pilot scale, occasionally with some field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although sometimes we do have supporting lab efforts here. Slide 11. We have 5 program areas, 4 in Under CERDIP, 5 are under ESTCP. The Energy and Water Program area is only under ESTCP, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Resiliency, and Weapons Systems and Platforms, are both under CERDIP and ESTCP and are managed jointly by a designated program manager. Slide 12. Our webinar today is focusing on research and demonstrations that were conducted under the Environmental Restoration Program area. And under this area, we have 5 main sub-areas of research: contaminated groundwater, contaminants on ranges, contaminated sediments, wastewater treatment, and risk assessment. Slide 13. Our webinar series is going to be highlighting research and demonstration efforts from each of the 5 program areas, and shown here are the next 5 that we have in the lineup. You can register for any of these webinars already. Just go to our website and you'll see the details there. Slide 14. Go to this link then and you can get more information about all of our upcoming webinars. Slide 15. And before I turn this over to Ms. Sullivan and Rula, I'd like to discuss our symposium. I'm very happy to announce that we will again be having our symposium in November 2017 this year. It will be at the Washington Hilton Hotel. Registration is now open. If you go to our website for the symposium, you will find details about the agenda, all the tech sessions, a number of short courses. So please take a look at that and get registered for the symposium. I hope you enjoy the webinar today, and Rula, I will send it back to you.
Thank you, Andrea. It is now my pleasure to introduce Ms. Maureen Sullivan, who is the Deputy Assistant Secretary of Defense for Environment, Safety, and Occupational Health. Ms. Sullivan is responsible for DoD's policies and programs related to compliance with environmental laws, greenhouse gas accounting and climate change adaptation, management of natural and cultural resources, and cleanup of contaminated sites, including those impacted by emerging contaminants. In addition, Ms. Sullivan oversees CERDIP and ESTCP, as well as the Armed Forces Pest Management Board and the DoD Explosive Safety Board. Her total DoD career spans 35 years. Maureen, we're very happy to have you. I'll turn it over to you now.
Thank you, Rula, and thank you, Andrea. Good afternoon, everybody, or good morning for some of you. I know this webinar is focused on PFAS, but I'm going to start off with talking about PFAS, PFOA, and the department, but I will touch on PFAS at the end. Well, let's start with EPA's Lifetime Health Advisory. I know all of you already know that EPA issued the Lifetime Health Advisories in May of 2016, and I hope you all appreciate that they are advisory for drinking water, but the structure is they become a to-be-considered number in the cleanup program or circle of responsibilities. Therefore, we, the Department of Defense, must roll them into our cleanup program. And what that means, the first step is we have to identify areas where we have there are known or suspected release. As of March of this year, we've identified 395 installations. Now, I want to note that I'm saying installations specifically. We have a lot more to do in the area of investigation. That does not mean we actually had a release at all 395, but there is a suspected release at some. So we don't know at this point how many, quote, sites we have. Second of all, the priority has been to cut off human exposure. So where we believe it's gotten into the drinking water, and we've validated that through sampling, our priority is to cut off the exposure through drinking water, whether it is to work with the community to provide alternative drinking water, turn off wells, assist them with cooperative agreements to install treatment systems. That was our highest priority to do that. Then the third step is following the normal CERCLA process, completing the preliminary assessments and site investigations. Then would move on to the remedial investigation feasibility studies, ultimately a decision, and ultimately a remedy. Now, when we get to the actual cleanup, a decision and a remedy is really going to depend on how it goes through the CERCLA risk assessment process and where it comes out in risk prioritization. Aside from initially cutting off the human exposure. So that's the structure we've put in place. Again, we're going to follow, once we've cut off human exposure through drinking water, we will follow the normal CERCLA process, the normal CERCLA risk assessment process, and work through our normal process working with the regulators to determine the full extent of the investigation, the remedial investigation feasibility study, ultimately to some sort of decision and remedy. So let me talk a little bit of budget because I think budget plays a big factor in all of this. And so I think it's important that you have the context of this. So as of December 31st, 2016, the department spent approximately $202 million in testing drinking water on our bases and doing this initial cleanup look to see where we might have human exposure and cutting that off. But here's the key point is none of that was programmed. We already had that money fully planned for certain cleanup activities. Most of it was cleanup. So that meant we had to reprioritize within the current cleanup structure. So some things had to be delayed in order to fulfill these requirements under there. Now, the key point I'm trying to make is there's no extra dollars in the cleanup program for this. There were no extra dollars in fiscal year 16, obviously. We already had, by the time when the EPA issued the Lifetime Health Advisory, it was well into fiscal year 16. We were in the third quarter. We'd already had appropriated dollars. We knew what our caps were and what we could spend. For FY17, it was already too late. That budget was locked. The President's budget request was on the Hill. So we, again, had to work within what the President's budget request was and what the Congress appropriated to us in the Defense Environmental Restoration account. But the problem is compounded because at that point, we had already started in developing our FY18 budget, and we generally already knew the top line. So even in FY18, we're within a set top line, and we're going to have to reprioritize, which puts further pressure on the overall cleanup program. The earliest we can start beginning to plan for an investment to respond to these lifetime health advisories is probably fiscal year 19, which we're working on right now. But the biggest question is, well, what does this mean? The adding of PFAS, PFOA, lowering the lifetime health advisories and the reference dose that comes with that enables us to go through the CERCLA risk assessment process. What does that mean for the department's liability? Now, we haven't run the numbers because we're still pulling the information in. We need to be further along in the preliminary assessment, site investigation, remedial investigation to be able to really do a full calculation of what this means. But by rough back of the envelope calculations, I figured it's going to add about $2 billion to our cleanup liability in the department, which is a lot of money. So then the challenge becomes, how do we make sure that we're figuring out the most efficient, most effective way to be able to address the requirements that are coming from these additional requirements that are associated with PFAS, PFOA. There's a lot there to do. So let me go on to say the big question I always have is, well, were we prepared, we the Department of Defense, and any others that were subject to this CERCLA requirement when EPA in fact issued the Lifetime Health Advisory in May of 2016? And I'll be honest with you, no, we were not prepared. But we responded, and I want to thank everybody for all the hard work that the DoD folks and our contractors have done to respond quickly and efficiently so that we were able to identify where there was human exposure and cut that exposure off as quickly as possible and start moving out through the normal CERCLA process. But there were still a lot of questions there, with a lot of unknowns in how we're going to deal with PFAS, PFOA. Remember, we're still early in the CERCLA process, in the PASI phases, so there's still a lot of work that still needs to be done. And there were many questions that we still have. What truly are all the sources? Where do we in fact need to look on our bases to determine if there was a release? What are the test methods? The test methods that have been developed for PFAS, PFOA are really for drinking water. Well, what are the ones for soil, for groundwater? How does PFAS, PFOA move in water? How do we communicate the risk associated with PFAS, PFOA? What are the real remedies? What are the most efficient ways? Well, and what is the best treatment method at the end? What is that best remedy? Is it appropriate to treat the groundwater, or is it appropriate to treat the finished water? So there are a lot of questions floating around still, and there's still a lot of work to be done in this area, and that's why I think it's so important that CERDP and ESTCP continue to focus on these. So that's our experience with PFAS, PFOA. So what does that tell us about the suite of perfluorinated alkali substances, which I'm not a scientist, I readily admit that. This has been a learning curve for me, and we have to be cautious that people use terms interchangeably. When we're thinking PFAS, PFOA, in some contracts, other people are thinking PFAS, and other people are saying PFCs, and they don't fully comprehend the difference between these three categories of compounds. I can tell you the department, we're getting a lot of pressure from communities, from citizens, from members of Congress to clean up all perfluorinated alkali substances, the whole suite of these. We've even been questions about cleaning up all PFCs, which for those of you that understand the technical, which is probably most of you versus me, we're talking tens of thousands of chemicals, but not fully understanding. So the questions when they say, well, you've got to clean up all PFCs, I must ask, based on what? How do we explain to communities that we're only cleaning up PFAS, PFOA, but not any of the other PFASs? What is the risks associated with these different compounds, and how do we communicate that risk? If we discover another PFAS in the water, what do we have to say about it in terms of the risk, and should we address it? So are we prepared if EPA is now going to regulate more of these PFASs? For example, right now there is a lot of discussion on a compound called Gen X. And so what is the question associated with Gen X? Are we prepared if EPA now suddenly decides that Gen X is also a risk? And are there common characteristics among these that would lead us to believe that we should be better prepared? A lot of questions, a lot of research that still needs to be done, a lot of technical information that has to be collected and analyzed and determined what we need to do. So I want to cut it off there. I want to express my strong appreciation for all the work Andrea and the whole CERDP team, all of the people that are participating in these research projects that they devoted to the challenge of PFAS, PFOA, and now to the suite of perfluorinated alkali substances. This research is key to our ability to have the right tools and resources at the right time. So thank you very much.
Thank you so much, Maureen. I'd like to remind the audience to please submit questions using the chat box on the left-hand portion of the screen. We have received a number of questions on the first portion of this presentation for you, Ms. Sullivan. And the first one is as follows. Can you please tell us what DoD has learned from the PFAS and PFOA site investigations conducted to date, and whether the estimate of the magnitude of the problem has changed as a result of recent site investigations.
Well, I'll answer the second part first. The magnitude hasn't changed because the site investigations really don't give us enough information to be able to do a full estimate of the liability. We really need to move on to the remedial investigation feasibility studies to get that full requirement. I'm sorry, you're going to have to, Rula, you're going to have to repeat the first part of the question.
Yes, the first part is what has DoD learned from the PFAS and PFOA site investigations conducted to date?
Well, one of the things that we've learned is that basically there's two general sources. Generally, there's going to be some others, but one is fire training pits. And the lesson learned from that is we already have probably those incorporated into our cleanup program, and it will be a matter of determining whether the remedy already in place for those fire training pits is appropriate for the addition of the PFAS, PFOA. The second is that the other likely source is crash sites, and we need to do work on that to figure out where we've had crash sites where the foam may have been applied. The other thing is that because of all the work we've done to date, we know a lot about the flow of water. And so that's really helped us because there's been so much work that's done on groundwater and understanding the groundwater underneath our bases. That's been a key tool to be able to help us figure out where things are flowing and what may happen as a result of these compounds getting into the groundwater.
Thank you. Can you please tell us what is unique about DoD's response to PFAS and PFOA compared to DoD's response to other emerging contaminants?
Actually, I would say that, I would say one of the things is what's been unique about it has been the response from citizens around bases, the widespread fear that's been associated with these two chemicals, and the way it was communicated out created a lot of uncertainty, which put us in a hard position of trying to explain what is the risk associated with these compounds. So that has forced us to be a lot more aggressive in trying to find out what are the right tools to communicate the risk. So there's been so much more external interest in this. That's driven more of the challenges compared to other emerging contaminants. The public interest, the media interest has compounded it, whereas we've addressed other emerging contaminants without such levels of attention in very routine ways.
Thank you. And one last question before we let you go. Does DoD have a process for identifying high priority PFAS and PFOA sites for possible remediation and/or management?
Well, the process is our standard circular process. Our program for a couple of decades now has been based on a nationwide risk-based prioritization based on a source, a pathway, and a receptor, following the circular process as I've mentioned. So we will be respectful and continue to follow that process. So the number one priority, again, the highest risk is where you have all three elements: a source, a pathway, and a receptor. And that generally is through drinking water, and that's been our number one priority, is to cut off that human exposure through drinking water. So we'll continue to follow that circular process in a thoughtful manner. We'll rack and stack. We'll identify the risk. We'll do our risk prioritization and roll it into the entire cleanup program.
Thank you so much. We appreciate your time, and our apologies for not being able to get to all the questions that came in for Maureen. It is now time to move over to Dr. Andrea Leeson. As I stated previously, Andrea is the Deputy Director of CERDUP and ESTCP, and also the Environmental Restoration Program Area Manager. Dr. Leeson has been with CERDUP and ESTCP since 2001, and before that, she was a research leader at Battelle, where she conducted scientific research on in-situ bioremediation, as well as the design and implementation of innovative treatment technologies for site remediation and industrial wastewater treatment. She received her PhD in environmental engineering from the Johns Hopkins University. Andrea?
Thanks again, Rula. And today what I'd like to do in my portion of the talk is to walk you through the various projects that CERDUP and ESTCP have funded since 2011 that have been addressing PFAS issues. I want to show you where you can get more information about the specific projects we funded. And then I also want to talk a little bit about the workshop we hosted in May of this year that addressed PFAS issues. Now, what you have in front of you on slide 19 is an overview of our program on PFASs. And what you see of the top half of this slide represents the statements of need under CERDUP that have been released. The bottom half represents projects that were funded under ESTCP. And of the CERDUP projects, the boxes under the CERDUP area, that represents generally several projects that were selected addressing the statement of need, whereas the boxes under ESTCP, those are actual individual projects. Slide 20. And across the top of the slide now, you'll see the link that will take you to a web page we have on our PFAS efforts. This slide, or this website will also have an interactive version of this graphic. And so when you see the graphic on our website, you can click on a CERDUP statement of need. You'll get a description of the statement of need, and under that you'll also have a listing of every project we've selected and funded under that statement of need. You can then click on individual projects and be taken over to the project web page. And from there you'll get more detailed technical information about the project. And those project web pages serve as a repository for any published document that comes out of the project. So please take a look at that website. It gives a good overview of everything we're funding under the PFAS issue. Slide 21. So what I'll do now is kind of walk through each of the statement of needs we've released and our thought process. Our first one we released in 2011. And this was released shortly after the EPA released the provisional health advisories for PFAS and PFOA. And we wanted to get a handle on this issue. And so the first statement of need we released was looking at both fate and transport of these properties as well as developing remedial technologies. We funded 3 projects under this statement of need, all of which are complete at this point. You'll see that the second one listed there has the term seed after it. And these projects are shorter ones. They are more of a proof of concept project. But the other 2 that were selected were full projects. Of the projects selected, the emphasis really was more on fate, transport, and occurrence of these compounds. And so if you could go to the next slide, you'll see that we released a follow-on statement of need in 2014 that also addressed in-situ remediation. And with this statement of need, we were very clear that we really were looking at development of remedial technologies at this point. We funded 5 projects under this statement of need listed below. And you can see that the first one was a seed with Dr. Mahendra at UCLA, looking at bioaugmentation with vaults. The other 4 projects were full projects taking 3 to 4 years. So given that these started in 2014, and generally when our projects say they started in 2014, they started later in the calendar year with our contracting process. So these projects are mostly still ongoing. I would expect most of them are finishing up sometime next year, but you can see that there's several different technologies that we're looking at this point. All of these, though, are at the bench scale level, and so we're still developing remedial technologies. Slide 23. Building on much of the work, though, that was done from the 2011 projects, we did start some work in 2015 under ESTCP. And you'll see 3 projects listed here. The last one that was started in 2017, which is field demonstration to enhance PFAS degradation and mass removal using thermally enhanced persulfate oxidation followed by pump and treat. That's just getting going. We're actually still in the contracting process, so we don't have a whole lot to talk about there. But if you could go to slide 24, I have a brief summary of the 2 ESTCP projects that we do have ongoing. This first one is on catalyzing rapid information transfer among key stakeholders on PFASs at our contaminated military sites. This was led by Dr. Jennifer Field at Oregon State with several team members. And the objective here was to expedite the transfer of knowledge about everything we knew about PFASs at military sites and get that out to stakeholders. This project is wrapping up now. We don't yet have documents posted on our website from this project, but that is imminent. I expect them to you'll start seeing them within the next month or 2. We have a frequently asked questions document that will be posted, and we have a short course being led by Dr. Field and her team at the upcoming CERTIP and ESTCP Symposium. And if you go to the symposium site, you can register not only for the symposium in general, but you'll want to register for the individual short courses. There is no cost for those short courses, but you will need to register because there will be limited space available. Slide 25 shows our next ESTCP project that we funded. This was started in 2016, and so this one, again, is just getting going. But what we're looking at here is John Cornick from NAVFAC Exwick out at Port Hueneme, California, is working on with his team to look at a number of different sites to get a better understanding of PFAS source zones, looking at differentiating between AFFF and non-AFFF sources. And they're also taking out the PIGI, particle-induced gamma ray emission spectroscopy, to look at it as a field screening tool. On this project, final documents and training material are due to start rolling out later in 2018, so you can look for that on the project web pages. Slide 26. So after we've initiated some of the ESTCP projects and looked at in situ remediation, we did go into looking at ecotoxicity. And we do look at ecotoxicity under CERTIP on occasion, particularly for compounds that are of particular concern at DoD sites. And we were careful with this statement of need, is that we went back and looked at what the data gaps are. And we ended up funding 4 projects very specifically to fill in some of those data gaps at a wide number of species, looking at avian, amphibian, reptiles, mammalian, fish, and invertebrate species. And these will help us to develop TRVs for our DoD sites. Slide 27, please. Now, way back in 2013, we had a strategic workshop, and this was on long-term management of our groundwater sites. And at these strategic workshops, they're basically a brainstorming session. And we were primarily looking at the issue of chlorinated solvents in groundwater, but definitely the issue came up of emerging contaminants and, what we needed to do with emerging contaminants at these sites. And so out of that workshop, we had funded a statement of need initiating in 2017 to look at mixed contamination at our groundwater sites. Of course, many of our groundwater sites are mixed with a variety of contaminants. And of the projects we funded there, 5 of them will be looking at chlorinated solvents mixed with PFASs. You can see there that there are a number of different technologies. We have reactive barrier walls and downhole recirculating wells, in situ chemical oxidation with bioremediation. We have electrolytic degradation with the electrobiostimulation. And then Chris Higgins at Colorado School of Mines is following some of his work looking more depth of fate and transport of some of these contaminants. And then we also have another seed effort. Again, that's the proof of concept looking at an electrochemical membrane. Again, these are 2017 projects, so they're just kind of getting up and off the ground. Slide 28. For 2018, we released 2 statements of need, and these projects have not been selected yet, so I want to just talk a little bit about what we were looking for there. In slide 29, we have the summary of the statement of need we released on improved understanding of PFAS source zones. And what we really wanted to do is kind of go back a bit and develop a better understanding of the key characteristics of the AFFF source zone areas. We wanted to better develop better tools and methods to characterize some of the key properties of these source zones. We wanted to understand the nature and permanence of PFAS retardation mechanisms and potentially how these mechanisms may impact natural attenuation or enhanced attenuation of these compounds. We wanted to fill key data gaps regarding biotransformation and transport of PFASs from the source zones. And finally, we would like to develop analytical or mathematical tools for prediction of fate and impacts. Next slide. Within this statement of need, we selected 5 proposals. Where we're at in the process is these proposals are subject to approval by our Scientific Advisory Board, and they will go before the board in October. If they are approved, and I certainly hope they will be, we will have more information about those projects on our website, hopefully by November of this year, so you can see what's going on. But this is our goal right now for the different objectives that will be addressed by those new projects. Slide 31. Our next statement of need we released under this area was to address in situ and ex situ remediation of PFAS contaminated water. And yes, this is the 3rd statement of need we've released looking at in situ remediation, and that really speaks to the difficulty of the issue. However, we are broadening it to look at ex situ technologies also. And what we made clear to proposers that it was vital that they considered the impact of common co-contaminants on the remedial process, because as I discussed before, most of our sites we do have mixed contamination, and really due to that and due to the complexity of dealing with these contaminants, we suggested that people look at treatment train approaches to address these contaminant plumes. Slide 32. We have selected 11 proposals at this point, and as I said before, these are subject to the approval of our Scientific Advisory Board. Again, that will occur in October. We hope for approval of all of these, and then therefore we should have descriptions of these projects available on the website I mentioned earlier by November. But you can see there's quite a few different technologies that are being investigated under these 11 selected projects. Slide 33. So that describes what we've done to date. Now I'd like to talk about the workshop we had in May. Slide 34. And we had released a number of statements of need of addressing this issue. We funded the different projects, and what we thought we would do is really gather together a bunch of experts to talk about where we're at. Here's what we've done. What do we need to do over the next 5 years or so? What are the areas we should be addressing with our resources? So in May, we had this workshop to address the issue of PFASs in the subsurface. As I said, our strategic workshops are essentially two-day brainstorming sessions. We have some introductory talks that talk about really what we know now, what some of our DoD services are experiencing at their sites to kind of set the stage. But then we go into our brainstorming sessions. We have people from academia, industry, the federal government, regulatory agencies, and we have people both on the research side as well as the people who are managing sites, as well as people who are dealing with policy on these issues. And we get them all together to talk about that. Roughly about 50 to 60 people attended, and from that we summarize the findings. Slide 35. So the link at the bottom of the page is the link to the summary report from this workshop. I really encourage you to take a look at that if you'd like to see what was discussed. But we had 7 major findings from the workshop. We discussed data gaps in fate and transport properties, ecological risk characterization, treatment technologies both from the aspect of research needs as well as demonstration needs, sampling and analytical procedure needs, measurement and prediction, and finally we got into the whole technology transfer issue. Slide 36. So under fate and transport properties, we identified 4 research needs, and you can see here they're identified as either critical priority and high priority. And for every need that was identified, we did prioritize them to that extent. Now, we didn't actually rank them from 1 to N. We were just doing broad categories of critical versus high. A need that got assigned a critical priority is something we felt really needed to be done immediately within the next 1 to 3 years, whereas high was something that perhaps could not be addressed until these critical priority needs were done. Often it was something that they needed to follow on to some of the critical priority needs. So under fate and transport, you can see we identified 2 critical priority needs. One was to further evaluate PFAS fate and transport processes, as well as the second one is to evaluate the influence of phase partitioning on fate and transport. And then we have the 2 high priority needs. One is to develop predictive fate and transport models, as well as the key parameters that are needed for such models, as well as developing leachability methods for PFASs in soils and sediments. Now, if you go to the workshop report, there is a more thorough description than I can certainly cover in this time frame, describing the intent of those research needs, and it presents a consensus viewpoint of the workshop participants. Slide 37. Ecological risk characterization primarily was research into the bioavailability, biomagnification, and toxicity of PFASs. This occupied quite a bit of the discussion. Given time constraints, I will leave you to read this and certainly go to the report to see more detail on all of this. Slide 38. We then talked about some of the research needs still existing for treatment technologies, both in situ and ex situ, as well as on-site technologies needed for concentrated PFAS waste streams, and then a little bit on specifically reductive technologies. Slide 39. Workshop participants felt a great deal was needed on sampling and analytical procedures, and so we have a fair amount of detail about those in the workshop report. Slide 49. Some specifics about the treatment technology demonstrations that are needed. Workshop participants felt more information was needed about thermal destruction technologies, as well as validation of different destruction technologies for their ability to treat these concentrated PFAS waste streams, and also of a high priority of side-by-side comparison of different treatment technologies, as well as side-by-side of in situ and ex situ PFAS treatment. Slide 41. measurement and prediction of the PFASs was of particular interest, particularly understanding mass flux of the compounds, slide 42. And then finally, technology transfer, something near and dear to my heart we spent quite a bit of time on. Here in the program office, we believe strongly that what we fund under CERTIB and ESTCP is really not money well spent unless we transfer that information out to the people who need it, to the end user community particularly. And so we discussed a number of ways that we needed to get this information out, particularly through a white paper at this point that can summarize really everything we need to know to date. So that is something that we're also looking at. Slide 43. And then what I'd like to do briefly is run through some of the resources. I've already mentioned the workshop report. It's now available on our website. I highly encourage you to look at that. This workshop report will help us form the basis for our future strategic vision for filling data gaps on PFASs in the subsurface. You can also go to our website to see a summary of our CERTIB and ESTCP efforts, and we will keep this up to date so it will be updated as we select new projects. And then in terms of future solicitations, we will be releasing a special CERTIB solicitation in mid-September. That is imminent, with full proposals due on that in late October. Please look for that. Our CERTIB regular solicitation will be coming out in late October for FY19 funding, with pre-proposals due in early January. And the ESTCP solicitation will come out in early January, with pre-proposals due in March 2018. After each of these solicitations, we will be holding a webinar to summarize the details of these specific solicitations, as well as answer any questions you may have about that. And I mentioned the solicitations here because certainly what we discussed at the workshop and is presented in the workshop report will be used to help guide what these solicitations will look like, and that's about all I can say about them at this point. Next slide. And so I will end here on our generic website describing all we know about PFASs and the CERTIB and ESTCP program. Rula?
Thank you so much, Andrea. We've received a lot of questions, but before we jump in, I just want to remind everybody that a copy of the slides of today's session is already on the website and can be downloaded now, and that the audio will be available in about a week. So the first question for you is from EPA, and it's a question about how CERTIB and ESTCP research funding efforts are being coordinated with EPA.
Well, we coordinate with the EPA a number of ways. Just within each of the program areas, we have a technical committee that helps us with both selecting new projects as well as reviewing and managing existing projects. And we have representatives from the EPA on those committees. And so the committee representative would then, be taking that information back to the EPA and letting them know what's going on. In our strategic workshop, we had a number of people from the EPA that participated in the workshop so that their voice was heard and they could take the information also back to the agency. And then finally, given the breadth of our PFAS program, we're going to be developing a smaller committee that will help us with specifically reviewing these projects, and we will have representatives from the EPA on that committee also.
Thank you very much, Andrea. A question about tech transfer and coordination. How do CERTIB and ESTCP see their efforts synergizing with other efforts, including ITRC's ongoing PFAS team?
We definitely try to work closely with other agencies that are working on this issue. We are working with the ITRC. We have representatives on the ITRC's new PFAS team. We had one of their co-chairs present at our strategic workshop. So, and then all of our PIs, we encourage them. Our representatives are aware of what we're funding, so they certainly bring the information to to the ITRC team in terms of what we're doing, but we also encourage our PIs occasionally to give presentations to the team where it's appropriate.
Thank you, Andrea. Are you in a position to tell us whether the scope of the call for abstracts and topics be narrowed to the topics discussed during the workshop, or will CERDP and ESTCP open funding to other PFAS topics?
So when you say the scope of the call for abstracts, you mean actually the solicitation, correct?
The funding, the call for proposal.
Yeah, I'm not in a position to specifically state what we'll be asking for. I will restate that I encourage anyone who's considering proposing to the program to look at the workshop and read it through to get a better understanding of what was discussed and what we've identified as key data gaps.
So if I may, I would like to go ahead and transition to the final part of our webinar, which will be presented by Dr. David Sedlak. Thank you, Andrea. David is a Malazanov Professor in the Department of Civil and Environmental Engineering at UC Berkeley. He is also the co-director of the Berkeley Water Center and Deputy Director of the NSF Engineering Research Center called Reinventing the Nation's Urban Water Infrastructure, which is also referred to as RENEW-IT. Since 2009, Dr. Sedlak has been studying the oxidative treatment of PFASs. He is the author of a book titled Water 4.0, The Past, Present, and Future of the World's Most Vital Resource. He serves as Editor-in-Chief of the American Chemical Society Journal, Environmental Science and Technology. David received a BS from Cornell and a PhD in water chemistry from the University of Wisconsin-Madison. And with that, I'll turn it over to you, David.
Great. Thank you very much, Rula. I'd like to follow on now with the introductory remarks we've heard and from Andrea's overview of the overall PFAS program at CERDP by telling you about some of the research that we've been doing on in situ chemical oxidation of PFAS compounds. And I guess to make a long story short, I think that if it was easy, there would already be a solution. So we've been chipping away at this problem for going on 7 years now, trying to understand whether it's possible to use in situ chemical oxidation to remediate these compounds. And the short answer to that is that we have some successes, but it's pretty complicated and it's challenging to actually implement in the field. And that's what we're hoping to gain more insight into as we move out to the field with our upcoming ESTCP project. And so today I'd like to give you an overview of where we stand, how we move through this process, and what kinds of remaining questions are out there. But I want to start with a background of PFAS compounds. I think some of you in the audience are probably very familiar with the nomenclature that people use, but some of you are still coming up to speed on it and are just trying to wrap your minds around PFOS and PFOA. And so I want to give you some overview on that. And then I want to talk about AFFF, these aqueous film-forming foams that are used at DoD sites and at civilian airports and for other applications, and to show you some of the complexity there. And then I'd like to kind of talk about how in situ chemical oxidation, or ISCO, can be used for it. It's a little bit of an alphabet soup, but something that I think will orient you as you get into this topic. So when I talk about ISCO, I'm going to talk about a stepwise treatment that we've developed where we first convert polyfluoroalkyl substances into perfluoroalkyl carboxylic acids, or PFCAs. So a little bit of a mouthful, but I think once you get the background of what I'm going to, could you go back to 47, please? And then I want to talk about mineralization of these compounds, showing that we can convert them into carbon dioxide and fluoride, and then tell you a little about the field applications. Slide 48. So this is an overview of the PFAS world, perfluoroalkyl substance world, and you can see that it's broken up into polymers and non-polymers. Generally, the polymers haven't been really the area of interest to us, but the interest has been in the non-polymers. Slide 49. And within the non-polymers, we think about the perfluoroalkyl substances and the polyfluoroalkyl substances. And they're differentiated by the fact that the perfluoroalkyl substances only consist of carbons that are fully fluorinated and some sort of acidic group, whereas the polyfluoroalkyl substances have alkyl groups on them. And those alkyl groups, circled here in red, are amenable to chemical oxidation and to biotransformation. And they're the things that can often be the place where chemical reactions start and ultimately convert the polyfluoroalkyl substances into the perfluoroalkyl substances. Those perfluoroalkyl substances are very difficult to degrade because the carbon-fluorine bond is one of the strongest covalent bonds in all of organic chemistry. Slide 50. Now, within this universe, you can see the perfluoroalkyl acids, or the PF acids, include the perfluorocarboxylic acids and the sulfonic acids. And that's where the majority of the attention has been so far. But you can also see under the polyfluoroalkyl substances many, many different kinds of substances. And these are the substances that often occur in AFFF or as intermediates in the production of polymers and can sometimes find their way into the environment. So slide 51. You can see that the perfluorocarboxylic acids and sulfonic acids are where we find our friends PFOA and PFAS. So these are the eight carbon members of these groups. But you can also see that they're not the only perfluorocarboxylic acids or perfluorosulfonic acids. That is, there are shorter chain compounds and there are longer chain compounds with the same carboxylic acid group at the end, but different chain lengths. And those different chain lengths will give these compounds different transport properties and different toxicity, but they will be similarly resistant to different kinds of biological and chemical transformation reactions, which makes them hard to remediate. And I think one of the issues that's coming up and that many of you are already aware of is that the manufacturers of AFFF a number of years ago started to reformulate their products to have shorter chain compounds. Those shorter chain compounds were put into the formulations because of a belief that they might be less toxic than the PFOA and PFAS, but they come with that extra price that they may also be more difficult to remove with adsorptive treatment technologies like activated carbon. And so when we think about oxidative remediation or reductive remediation or any kind of transformation of PFAS and PFOA, we have to keep our eyes open for the possibility that we're converting them into shorter chain compounds. That might also be a concern. Even if they're not currently regulated, I think that's everyone's concern, is that if you start remediating for PFAS and PFOA, you don't want to form a transformation product that is transported more readily and maybe is later found to have significant health consequences at the concentrations present after remediation. Slide 52. So with that in mind, that brief primer on it, and I think you could see there was a reference in those previous slides to a paper that was published in 2011 by Buck et al. For those who want to kind of see all the details of how we talk about these compounds. I want to turn the attention now to the treatment of perfluoroalkyl acids with persulfate. And if you're not familiar with in situ chemical oxidation, or ISCO, it's basically the process of putting a strong oxidant into the subsurface and letting it decompose to form reactive radical species. In the case of persulfate treatment, we're converting the persulfate into sulfate radicals, and sulfate radicals are very reactive and relatively unselective oxidants. The other main type of ISCO technology that people have been considering for remediation of PFAS compounds is hydrogen peroxide, which decomposes to hydroxyl radical. But we were interested in persulfate because there were some reports that persulfate or sulfate radicals were capable of transforming some of these compounds, at least in very clean, pure systems. So what I'm going to talk to you about today, first with PFOA and PFAS, is their conversion into shorter chain compounds and mineralization. But remember, what I'm talking about is also relevant to the longer and shorter chain perfluorocarboxylic acids and perfluorosulfonic acids. Slide 53. So the first place you start is looking at deionized water. So the purest system you can come up with, deionized water. So these are results of some experiments where we put in a relatively high concentration of persulfate. You can see there 50 millimolar. This is really high, but it's comparable to what's often found during in situ chemical oxidation, where we put in even higher concentrations of persulfate. And it was, we heated the water to 85 degrees centigrade to convert the persulfate into sulfate radicals. So thermal activation is often used for persulfate. There are other ways of activating persulfate. They all make sulfate radicals. We did this at 85 degrees centigrade because all of the persulfate is converted into sulfate radicals within a few hours, so it made it convenient to do the experiments in the lab. And this first experiment was done without any buffer. And so when the persulfate decomposes, it forms sulfuric acid, and the pH drops rapidly to values below 3. And what you can see happens here is that as the persulfate disappears, the PFAS compounds, or the PFOA, disappears. So the PFOA was almost all gone within about 2 hours, and we started to form the shorter chain perfluorocarboxylic acids like the heptanoic and hexanoic and the C5 and C4 compounds, the pentanoic and butanoic. And then overall, we saw a 75% decrease in the PFAS compounds, and that missing perfluorocompounds was showing up as fluoride. So we measured fluoride by ion chromatography, and we closed the mass balance. So we were mineralizing the PFOA by first taking it into shorter chain compounds and then all the way to fluoride and carbon dioxide. Slide 54. But that's not, just because you can do something in distilled water doesn't mean you can do it in the environment. As we all know, groundwater tends to be buffered by carbonate. And so if you have a carbonate buffered system, the pH will stay at 8 for quite a while during the ISCO treatment. And so we repeated this experiment with different buffers, in this case borate buffer, phosphoric acid buffer, or sulfuric acid as a buffer. And what you can see here is that if the pH didn't drop below 6, we saw no transformation. Slide 55. And when we had the unbuffered situation, we saw good removal. So we had to get the pH below 3 for these reactions to result in transformation of the PFOA. And I'm not going to have time to get into the mechanism here today, but that has to do with, we think, with the protonation of the PFOA at very low pH values. So in order to be effective in remediating PFOA with sulfate radical, we have to get down to at least a pH of 3, and when we can drop the pH down around 2.5, the reaction becomes much more efficient. Slide 56. Natural waters also contain chloride, and we know that sulfate radical reacts with chloride, often forming chlorate as a byproduct. And what you can see in this experiment is that if we have high concentrations of chloride present, we also don't see conversion of PFOA. And you can see here that when we start with 50 millimolar persulfate, we have to, and we had chloride concentrations of 50 millimolar, we get very little transformation. That's because the sulfate radical is preferentially reacting with chloride. Now, most natural waters, most groundwaters that would be candidates for drinking water have chloride concentrations that are considerably lower than 10 millimolar, so it's not an issue. But if you had a brackish groundwater or a source zone with very high chloride concentrations due to disposal of some other contaminant, you'd have to add enough persulfate to convert that chloride over to chlorate before you'd see any mineralization. Slide 57. We also decided that, just because it works in the presence of chloride and we understand the effects of pH, we would want to know if the presence of aquifer solids affects the reaction. So we used some authentic aquifer sediments in a slurry of 200 grams per liter. And what you can see here is that when we thermally activate the persulfate in the presence of the slurry, the persulfate goes away. That's the upper slide. You can see we had 2 different doses. So after about 7 hours, we added a second 50 millimolar aliquot of persulfate and watched it go away. And as that goes away, you can see the PFOA disappears, as you might expect. And so the presence of aquifer solids decreases the overall efficiency of the reaction because some of the PFOA is associated with the sediments, but it doesn't stop the reaction entirely. So we're pretty confident that provided that you can achieve the appropriate pH values, you should be able to use this technique to mineralize the PFOA or the carboxylic acids. Slide 58. But unfortunately, this technology does not work for PFAS, and so, or any of the other sulfonic acids. So here's an experiment going back to deionized water, the most simple matrix possible. When we have PFAS in deionized water, even if we let the pH drop below 3, we don't see any conversion of the PFAS or any of the other perfluorosulfonic acids. And so this in situ chemical oxidation with sulfate radical is only relevant for the carboxylic acids, not the sulfonates. And I'll come back to that as we talk about the sulfonates that are present in AFFF. Slide 59. So let's do that. Let's talk about the difference between working with solutions of PFOA and PFAS and actually trying to remediate AFFF contaminated sites, because that's what we're mainly interested in, is actually going to the sites that have AFFF present, not just those two components. And what you'll see here is that the presence of AFFF complicates the system because there are other polyfluoroalkyl substances present. There are also other organic compounds that could scavenge the different radical species and lower the overall efficiency of the treatment process. Slide 60. So first of all, it's important to recognize that when we talk about AFFF, not all AFFF is created equally. There are two main, what I'll refer to here as flavors of AFFF, and they were both used in the military specs and in commercial airports for firefighting. And so there's one that was produced by the 3M Corporation primarily because they had the patent for electrochemical fluorination. And then there was another one that was produced by a variety of other manufacturers, primarily the Ansell Corporation, but a few others, that involved the use of fluorotelemers or the fluorotelemization process. And if you look carefully at the composition of the 3M AFFF, you'll see that there certainly is the PFAS and the hexasulfonic acids present. So there are the perfluoroalkyl sulfonates, and there are small amounts of the carboxylates, but you'll see a lot of other compounds, polyfluorinated alkyl substances that are sulfonamide-based compounds, and we'll take a look at those. And then in the Ansell and the other types of AFFF produced by fluorotelemization, you'll see these fluorotelmer-based compounds, or these compounds where you have an alkyl group at the end of that perfluoroalkyl chain. Slide 61. So starting with an Ansell AFFF, this one is one that we got from some of our partners in the Department of Defense, and this particular one had a compound called Lodine, shown here in this figure, a 6,2-fluorotelemethioamido sulfonate compound, which was prominent in it. And what you can see is when we subject it to heat-activated persulfate under the same conditions that we looked at for PFOA and PFAS a few moments ago, you see a rapid conversion of that compound into a suite of perfluorocarboxylic acids, the C4, 5, 6, 7, and 8 compounds, and then those are slowly mineralized, as we saw with the carboxylic acid. So what you see is that it's very quickly you can break that telomer group shown on the right-hand side of the molecule, and the product of that are the carboxylic acids. Not a lot of PFOA in this case, but the C7, 6, 5, and 4 acids being present. And then those are mineralized or converted to the shorter chain compounds, just as we saw with PFOA. Slide 62. if we turn our attention to the AFFF produced by 3M, which has the sulfonates here, PFAS being the main one, but also a lesser amount of the hexane sulfonate. What happens is just what we saw with PFAS in the pure solution. So there's nothing special about the hydrocarbon surfactants or the alcohols or the other components of AFFF. We still can't break down the sulfonates by activated persulfate. Slide 63. But there are some compounds in the 3M AFFF that can be converted to carboxylates by sulfate radical. So you can see the structure of one of them shown in this slide. And when we subject it to heat-activated persulfate under the same conditions that we've been looking at in the previous slides, we see that it's very quickly converted to the carboxylate compounds, in this case the C6, 5, and 4 carboxylates, and then those are mineralized because we have an unbuffered system with a pH drifting below 3. Slide 64. And so kind of what we've learned from this research is that it is possible to remediate AFFF contaminated groundwater with heat-activated persulfate, but it requires a very specific set of conditions. It requires that you drop the pH below 3. It requires that you not have a lot of chloride around, and it will not work on the sulfonate compounds. And so we're planning to go in the field in the near future as part of this ESTCP project with the U.S. Navy and Geosyntec. And the way we're going to do that project is we're going to identify a source zone with AFFF contamination and first heat the sediments by hydrogen peroxide ISCO, which is an exothermic process which will heat the aquifer solids in the groundwater, and will drive some of the polyfluoroalkyl substances into the corresponding carboxylates. And then we're going to add persulfate, which will acidify the aquifer and drop it down to pHs of 3 and below for the perfluorocarboxylic acid mineralization. And if you think that sounds challenging, I think it is. I think this is the kind of thing that one does in source zones where you can overwhelm the buffering capacity of the sediments by titrating out any carbonates or buffering minerals present in a small area by generating all of this sulfuric acid, and then neutralize the groundwater before it moves off-site. There's also scope for some future applications. I think that this technology would be especially well suited for sites where either perfluorocarboxylic acids are the main contaminants, for example, manufacturing sites that only contain things like PFOA and its shorter chain partners, or at sites where the AFFF contamination was only from the Ansel products or the products of the fluorotelomerization process, where you don't have those 3M products around which were rich in the perfluorosulfonic acids. And we're also investigating the possibility of coupling this ISCO treatment method with bioremediation, and that's in partnership with Lisa Alvarez-Cohen, who's the lead PI on the CERDIP grant, and thinking about whether either using bioremediation to get rid of the hydrocarbon surfactants and the alcohols before ISCO makes the process more efficient, or if there's any possibility of using ISCO before bioremediation. Slide 66. Sorry, 65 I meant. So in summary, I showed you that persulfate or hydrogen peroxide ISCO, I haven't shown the data, but we've done those experiments. In these processes, you make sulfate radical and hydroxyl radical. These radicals can convert the polyfluorinated compounds into the carboxylate compounds. And so this is kind of a way, if you want to think about those polyfluorinated compounds as precursors of the perfluorocarboxylates, we're essentially driving the precursors into the perfluorocarboxylate compounds. even if you just stop there, it does have some benefits in that it simplifies the remediation process. You don't have these other compounds out there that have different fate and transport properties that will slowly undergo conversion into the perfluorocarboxylate. So it could make it easier just to manage a site if you know that you've driven everything to the corresponding carboxylates and the sulfonates are there, and then you could remediate them by some other kind of ex situ treatment technology. I've also shown you that persulfate, which is activated into the sulfate radical, can mineralize the perfluorocarboxylic acids, but only at pH values below 3. And that is a challenge, obviously, for in situ chemical oxidation, because you have to have a site that doesn't have a lot of potential to buffer against those low pHs. So you need a sandy aquifer, basically, where you can titrate out any acid neutralizing minerals present. I also told you about this interference from chloride, which would be a problem in brackish groundwater. And then finally, the real benefit here is it may be a means of in situ remediation of sites where you only have the perfluorocarboxylic acids, or where you only have contamination with the AFFF produced by the fluorotelomerization process. And so again, these limitations here are important to point out. This is not a magic bullet or an absolute solution, because many AFFF contaminated sites have the perfluorosulfonic acids. Many places, in addition to using the AFFF from the fluorotelomerization process, also have the AFFF from the 3M product. Many sites have high alkalinity or have sediments with a lot of carbonate buffering potential, and of course there are sites where you'll have high levels of chloride in the groundwater. Slide 66. So a couple of final thoughts here. First of all, we're very grateful to CERDIP for providing funding for this project, but the work that we did was required a lot more effort and time than just the one CERDIP grant that we've already worked on. In particular, I want to acknowledge the support from the UC Berkeley Superfund Research Program, which is funded by the NIEHS, and also my graduate student, Tom Bruton, who did most of these experiments, was funded by a National Science Foundation Graduate Research Fellowship. And I thought I'd close with the poem, or rather the song, The Impossible Dream, because that's where that idea of fighting the unbeatable foe comes from. I really consider the PFAS compounds to be a real challenge, and there are days when it really feels like it's an unbeatable foe. But I think that we really need to follow this quest, because it's so important to clean up these sites, and an in situ treatment method is going to be a lot more cost effective than going with pump and treat. So slide 77, or the next slide, is the website for the CERDIP program and my email address if you need to get in touch with me. And I think with that, we move on to the third Q&A session.
Great, thank you, David. Let's start with one specific to the technical portion of your talk. In your experiments, you used persulfate as the ISCO reagent. Will hydrogen peroxide or other oxidants work too?
So we do use the hydrogen peroxide, or we're planning to use the hydrogen peroxide in our fieldwork as part of the ESTCP program, and it will produce hydroxyl radical, which will convert the polyfluoroalkyl substances into the perfluorocarboxylic acids, but it will not degrade the perfluorocarboxylic acids. So we'd get stuck with the carboxylic acids and sulfonates in the groundwater after that treatment.
Thank you. You conducted many of your experiments at very high temperatures, at 85 degrees C. Will you still be able to degrade PFASs at lower temperatures?
Yeah, so in this case we used high temperatures, and there are times when persulfate is activated by high temperatures, for example with steam injection or with aquifer heating with hydrogen peroxide. But generally speaking, you don't necessarily reach a temperature of 85 degrees centigrade. This was a temperature that was convenient because we could finish the experiments in a few hours. If you lower the temperature to something like, 45 to 60 degrees centigrade, you still get rapid conversion of the persulfate into sulfate radicals. Instead of in 2 or 3 hours, it might take a day, and that's fine for an ISCO application. And we expect the same sorts of reactions because the reactions of sulfate radical are not strongly temperature dependent.
Great, thank you. And this is a question from the U.S. Army Corps of Engineers in Seattle. By using persulfate instead of another oxidant, are you concerned that residual sulfate levels in groundwater may exceed secondary drinking water levels?
So sulfate is certainly a constituent of concern for drinking water because there are health concerns associated with high levels of sulfate in drinking water. If I recall, it's in the maybe 100 milligram per liter range, and with these high levels of persulfate that are used in ISCO, you can generate high concentrations of sulfate. This treatment technology is most relevant to source zones, and so the high levels of sulfate that are generated are generally diluted away in the aquifer after the treatment. And if it really became an issue, one could take the water from the ISCO treatment and dispose of it separately. The other issue here is that as part of this neutralization process for the sulfuric acid containing water, we're considering a step where we pump the water into a bed of calcium carbonate forming gypsum, calcium sulfate, in an exchange reaction, which would remove the sulfate from the water.
Great, thank you, David. A question from the U.S. Navy. Do you have any insights on why the sulfate radical does not break down PFAS? Is it a mechanistic barrier or an energy barrier?
Gee, it is a tough question, and I think even the mechanism through which the perfluorocarboxylates breaks down is still a little speculative. It seems that the sulfonic acids are more amenable to reduction than oxidation, and there aren't too many treatments that seem to be capable of oxidizing them. So I'm assuming it's a mechanistic issue, and you don't have the same pathway for decarboxylation when you have the sulfate present. So when you react the perfluorocarboxylates with sulfate radical, you get the loss of a CO2, and the same kind of reaction doesn't seem to happen with the sulfate.
Thank you, David. And one last question from one of your previous students. Do you have a pilot study site already selected, and if so, what are the site conditions like?
Well, great to hear from an old student, and that they're working in this area, because we need all the people we can to try to tackle this problem. We have a couple of candidate sites, and we're in the process of collecting some aquifer solids from them. The main criteria that we're looking for is, first of all, shallow depth to groundwater and depth to contamination, because we want to keep it relatively simple from a hydrogeology perspective. But we're also looking for a site that doesn't have high levels of chloride, so isn't under the influence of seawater, and where the levels of acid neutralizing minerals like calcite are low in the soil. So we kind of are going to do some titrations to figure out how much persulfate we have to add before we can drop the pH below 3 in the source zone.
Thank you. And one last question just came in from the U.S. EPA. Will the proposed pilot, will you be able to reverse the conditions in the subsurface when you're done with the pilot study, especially as they relate to pH?
Yeah, so we have plans, and I kind of referred to them a little bit in a previous question, that either we're going to, as we do the ISCO pump and inject and recover of the water, final neutralization step where we pass this acidic water over a bed of calcite to neutralize it and remove the sulfate. But even if some acidic water escapes from the site, we know from research that people have done on CO2 sequestration that the acid in the subsurface will be neutralized as the plume moves off site and encounters carbonate-containing minerals. So even though it is a pulse of acid going into an aquifer, I'm pretty certain that any acid that we don't actually capture will be neutralized in the aquifer before it gets too far down gradient.
Thank you so much. And as we wrap up this webinar, just one quick question for both you and Andrea, and we'll start with Andrea. What is the single message that you would like to leave our audience with today?
Really, I wanted to make people aware of the breadth of what we are doing with the PFAS issue, as well as the results from our workshop report, since that is directly applicable to upcoming solicitations under both our programs. So I'd ask people to go to our website, take a look at our PFAS page, as well as the workshop report.
Thank you, Andrea. And David?
I'd like the participants to recognize that there's not an absolute perfect solution for in situ oxidation or in situ treatment of PFAS compounds today. We're at a point where we have a means of remediating a subset of the compounds under admittedly challenging conditions, that is acidifying an aquifer, and that all of this great research that CERDIP and ESTCP has in the pipeline may provide us with some additional alternatives, but it's going to be a long battle to fight.
Great. I'd like to thank you, David and Andrea, for your wonderful presentations. And I'd like to remind all of you that our next webinar is on October 5, and it's titled New Resource Conservation Insights to Desert Environment. This webinar will feature two speakers, Dr. Dave Lytle of Oregon State University and Dr. Christopher Castro of the University of Arizona. Registration is already open for this webinar, so please visit the CERDIP and ESTCP webinar webpage to register for this and other future webinars through the end of 2017. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you can please take a moment to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you so much for your time.